All right. Anyways, I wish you guys all the best. And so this will be our last hurrah here from a class perspective. Um, all right, let me do this. Let's do it. I guess the other thing I'm happy about is that I think my computer is going to make it. Um, I was worried probably about 2 weeks ago that my computer would not be making it um, throughout the rest of the quarter, but it has. So that's a win. And it looks like my internet is working today. Um, so we'll just kind of call that a win and say that it could have been a lot worse. Um, so tall buildings. Just kind of taking a look at some profiles. I know we're short on names here, but we'll get to some of the names. It's not too much exactly as to what all they are or where they're located. But I don't know if you may have seen some of these buildings, but this really is just here to give us a feel for the. Let me get a pen on this. Give me 1 second. Sorry. All right, now we're moving. So really just to highlight the height of these buildings. And we're talking like right here, that's half a kilometer. That's pretty high. And the tallest building's up here about 800 meters. There's one that's going to be completed. That'll be over a kilometer high. So we'll talk just about some of the structural characteristics and some of these buildings themselves. Early on, we'll look at some of the history. Early on, the progression was most of these buildings were in the United States, and now they have moved to other parts of the world or have shown up in other parts of the world. So, like I say, this will be a little bit more popcorn type of content. So, currently, the tallest, which is over 800 kilometers, is in Dubai. And we'll talk about what we see here. You see a tapered, sort of a tapered structure here. There's steps, so there's sort of tubes going on, and we'll take a look at the cross section of this and the shape. But there's so much in terms of just that we're going to talk about today that deals with the shape of the structure, and then how the gravity and the lateral are really integrated into that shape. So just sort of remarkable. We'll talk a little bit about the concrete that's used. A lot of times you'll end up with concrete on the bottom and then steel structure on the top. And then we'll talk about the different types of systems that are in these tall buildings. So Project 3 was trying to push you in a little bit to get us, about 100 feet. Clearly a little bit short of this one. It almost looks like a cartoon. Like if you look at these buildings, they're so massive from where they sit. This is the one in Saudi Arabia that will be completed, I believe, this year. And the size, it's over 1,000 meters. It's an observatory, but then, it's, oh goodness, 10 meters per second for the elevator speed. Clearly, it's going to take you a while to get all the way to the top of that thing, but just sort of amazing. And they talked about with, the slowing in the construction process due to the COVID. So this one will be the tallest, and it's actually taken it started in 2013, and I believe this building was completed in 2010, if I know correctly. Might be a little off there. Here's a little bit in North America, and this is back a little ways, back in 2016. But looking at some of the states, let me just keep this, there's Riley. Um, Looking at some of the states and numbers of buildings, and then average heights, which really doesn't account for, well, the most part accounts for the fact there's so many buildings, but over here kind of gives us the tallest in each city. Um, so that's obviously it's no longer the Empire State Building, but the the U.S. Bank Tower in Los Angeles, and kind of looking, it's not all the states, but kind of get a little giggle. Um, I have been through Santa Fe once before, um, on my way to Albuquerque, I believe. And so the area, or the location of these buildings here, just in the United States. Um, this is kind of this is a neat one, and this is sort of the history of. You guys are in my way here, my little Zoom thing. My computer's starting to heat. All right, I'm just going to leave that there. I can't quite see the bottom. But anyways, it gives us a vertical scale over here in terms of the height. So there's the building in Dubai. That was 2010. And so these are the tallest buildings. Kind of interesting as to what they call the tallest, in terms of that antenna that could be on the top. So looking back, here's about 1900, the tallest building. And then it's kind of gap here. And so we'll talk about the 1960s, which was really where the technology showed up to sort of build these in a different concept than the Empire State Building and the Chrysler Building. But it kind of shows, the change, how the step occurred in terms of adding height to the buildings, and gives you a little bit of a history here over time. Notice these are all in the United States, and then it starts to end up in Kuala Lumpur, and then Taipei and Dubai. We'll talk about this one at the very end. This is a very interesting building in Taipei. So again, this is just the overall history, and then also giving you a little bit in the change, the relative change in the changes in the tallest building as when it got supplanted from the previous year. So this obviously has been replaced as well. So what's the sort of the big deal, besides the fact that they're just so tall? What's kind of the big deal about this whole thing? So there's some things to keep in mind here. One, and we talked about this with cladding, but anytime you do something on a large repetition scale, the economy of each component becomes accentuated because it's going to be used so many times. And the other thing is that the structure and the building, like all of it is used from a structural point of view. And what I mean by that is really more from a lateral perspective. Of course, the entire building has to account for gravity loads, but as we've laid out structural systems in our buildings, it wasn't like every inch of it didn't need to be used for a lateral system. And so that's what your project 3 and 2 we're trying to have you think about, and what you need to provide based on the demand and the capacity. And essentially with these tall buildings, there's so much demand that the entire building becomes sort of useful structure. And I mean that in a lateral sense. And the stability issues really are dealt with on a global and a local setting. I'm going to go ahead and do this. My machine is nicely so far, not running too much. Sort of funny, if I just don't do anything for like an hour before on my machine, then it can sort of last longer. So anyways, I don't think this computer is going to make it through the summer for me, but it's neither here nor there right now. So uh, other thing to remember, and we've seen this, obviously with the lateral and with wind, you guys would know that the loads increase, as you move up the structure. The wind pressure increases from a seismic point of view. The issue is that you end up with higher accelerations at the top, and mass times acceleration is what creates that force. So it gets accentuated with a tall building because you end up with sort of a whipping effect that's occurring up here as opposed to all the way down there. So and it turns out that the wind often will be very it'll be quite, I'm going to erase that and make it look very good. Sorry. It governs a lot of the design, but we'll also talk about some of the seismic response in the higher modes that show up. So, and then obviously the other thing that occurs, when you've got something so high, is just massive, gravity loads. So, yeah, I can't even write that. So this is how you end up with that, a need for that higher strength concrete. The stuff in the manual you've got, we're dealing with like 4 KSI or 6 KSI concrete. So obviously increases the cost. So from a structural vibration point of view, sort of a very interesting topic as you deal with structures that get taller, the response moves away from what you would call flexure. And so we've talked about this, in our lateral analysis, talking about the flexure, of a shear wall, and treating it like it's a bending beam. If you sort of turn your head to the left like that, right? You kind of see there's the quote, the wall, there's the cantilever, and there's the load. It's just, oriented differently. You end up then with frame structures, which you're going to end up with these high-rise buildings. Is you get this shear beam response, and so now it's neither one is exactly as clean as just one or the other, but as the height goes up, we get a different response and a totally different shape. Here you've got the quote, the flexure, the bending beam. I don't know why I did that. That doesn't look very good. And here you get a totally different shape. This would be a shear beam. If a beam were dominant by shear, it would deform like this. So what you're seeing is deformations that are more shear-like. So my machine just looked at me or said, the internet is unstable. This is the last day that I'm gonna have to deal with that. So pretty happy about that. So bending, shear, and it's gonna be some form of a combination of the two. So we get this really different response that shows up. And the systems, there's several. I'm going to kind of focus on these 6 here. So and really this is what showed up in the 1960s, was this, framed tube system over here in A, and there's often a lot of hybrid that goes on. So it's not often just this clean, but there'd be bundled tubes where there's sort of multiple tubes sort of held together, not just kind of one huge tube. And there's also tube in a tube, where we've got a core here and then an outer, tube itself. A diagonalized system, I think you can probably predict as to what pictures we'll see if you were not looking ahead. This core in the outrigger system is quite interesting, and that's really strong as to what's been how some of those buildings recently became so big, using this strong sort of concrete core. And then these huge outriggers that, again, those are not on each floor, but these large outriggers that then sort of, take this very slender core right there and then give it more stability, without making the core bigger. And then a, sort of a hybrid system, that would be a combination of them. And we'll also see, like we saw in the, tapered, we'll see sort of tapered system, bundled tube sort of, representation. So not just an absolute rectangle. So a tube system is just sort of a pioneering discovery. I'm going to let you just kind of peruse that for a second. I'll give you a second here. We lost one. So the old World Trade Center was this tube system, um, very dense sort of columns and beam, on the outside. Could be concrete, steel, composite, closely spaced columns, tied together with spandrel beams. That's what makes that rigid frame. Those very stiff, because those beams were so small. They're very stiff. And so what that does then is leave the interior for, um, mainly for the gravity design, the gravity loads. They don't have to deal with lateral loads, so it, keeps it all on the perimeter. Um, so here's a couple. So the World Trade Center, which I didn't want to put in, just from a visual for it. Here's a bundled tube, be the Sears Tower. You can kind of see those tubes that are all together, bundled with step backs. Um, you know, not to bring everything back to the Eiffel Tower, but and we saw that a couple. I'm going to do this. I'm going to slide back here. So in dealing with the uh, cantilever beam analogy and the moment diagram, and so that required stiffness. Then, right, that mimics the moment diagram. So that's why those buildings will get a little more stable, a little more beefy at the bottom. Diagonalized system would be the Hancock Tower. That would, obviously you could see those. And it's quite a bit of taper on that building as well. So there's a New World Trade Center. It's a hybrid system, concrete core with a perimeter steel moment frame. So that's a look at a hybrid system. And then here are some, obviously you can't see them, but the core and the outrigger system. The two towers is the one in Kuala Lumpur. And so this is not the outrigger right there. That just connects the two. So that's not the outrigger. The outrigger is inside. They've got a concrete core inside that would be, extending all the way up, and then the outrigging to the external on the building. And so that's the to the perimeter columns. So if I remember right, that was Mission Impossible, I think. So then here's the picture of that tallest building that we've got, and kind of look at the geometry. So this one, you see the hexagonal core right here, right, and then offshooting from it, this buttressed, right? Those act like buttresses to the core. And this is actually a steel on concrete building. So here's a look at all the cross sections, and as they decrease as they move up the building. And again, just keeping in mind that increased stiffness, increased stability down here. So quite an interesting huge building. That's, like I say, that's currently the tallest, which gets over 800 meters. So just a couple more here. I said we'd be brief. And so, from a analysis point of view, so everything that we've done from a vibration, which would really be seismic more so than wind, but I keep drawing that, that triangular distribution. And what this does is it mimics the primary response of the building. And so for shorter buildings, the response is going to be primarily in what's called the fundamental mode or the primary mode, the first mode. And so here would be a picture of a mode shape for a taller building. And when that building becomes excited in a vibration, in a vibratory sense, other modes can show up, especially when the input down here is random or random like in an earthquake. So here would be a second mode, and we get, it's called a zero crossing. And so if you let me go back over here, this thing would go back and forth and back and forth. I'm going to use the word relatively slow. It would be very fast, but this would be more, it would be increased speed. I'm just going to call it. You know why I'm doing this. Losing it, folks. There we go. And so this would have higher accelerations, and there are things that are called participation factors. And so it's just that the higher modes don't participate as much in smaller buildings. You can get higher modal participation in taller buildings. So this modal analysis, this would be the third mode. And so you see how, this is the primary mode. This is where the bulk of the deflection would occur. But these are smaller accelerations than they are in these modes. So you end up with the necessity to analyze more modes. So it's much different than what we do with a single profile, the way that we distribute our, this would be more for earthquake, but the same could be said for wind, and as the wind were to blow, and as other modes were to become excited in the building. So when I was at graduate school, there was a library on our campus that there was a shaker on top. So they would actually go up and shake. It was about an 8-story building. So there was a shaker up there. It was connected to the building. And so we would shake it, and depending on how fast you shook it, it would either respond, oh goodness, that's horrible, in the first mode, or if you shook it faster, then it would respond in the second mode. And you could literally feel these. There was a stairwell on the side, and as you walked up, you could feel it. And on the top, there was little antennas, about an 8-story building, but you could see them. They would go back and forth, back and forth. So the vibration is quite real. So here we are, drum roll for the last slide of the quarter here. So the way that the some of these buildings, not all of them, but there's a technique for these buildings to help mitigate some of the vibration, and it's called a mass-tuned damper. And so this is the big mass, and it is tuned in to the movement of the building. And so when the building moves this way, this mass is going to try and move that way. So the big inertial force is then combated by inertial force inside the building. So this is a way that you can, again, depending on this, mostly for wind. And so this would then just be reacting. And you can have in these buildings, you can have movement up here. Like go back to my library just a second ago, and people would complain in the library when we would shake it, and sort of rightfully so, especially on the 7th floor. And so same thing here is that this building could start vibrating, and nothing is, nothing is in danger in the building, except the occupants, which, tend to get a little sick or motion sickness when this occurs. So that's a, pretty neat. This idea of damping is that idea is to remove or to sort of take away the vibration once it occurs. So a big, huge mass up there. Most times they do require power. So if there were a large event and power to go out, then that wouldn't quite work. But that's that building in Taipei. So one final drum roll. We'll say thank you. This is the end. Like I said, I will be available tomorrow 10 to 12 and Saturday 10 to 12. I will stay here, take a little break, and then I'm gonna stay till about 5:30. So give me till about 4. Actually, you know what? I'm just gonna stay. I will just ride this thing out. So thank you guys, and let me turn my share off. Say one last. So thank you guys. I hope you guys have a good end to your quarter, and stay in touch if I can help you at all.
I did not get the last part. I did not get the last part.
Oh, at all. Which part? I'm sorry.
Just the last part about the end of this class, like about 5 minutes or something.
Did it all go out? Let me turn this on here 1 second.
It kind of got choppy on my end too, so I wasn't able to like hear like after like the lecture ended, like what were.
Oh, okay. Okay, just the very end. Okay. So I was saying, sorry. I will have office hours 10 to 12 tomorrow and Saturday, and I will stay around right now after class as well. So I think that was all. That actually was all I was saying at the end. So thank you guys. Good luck.
Thanks, Andy.
Thank you.
You're welcome.
Thank you.
Mm-hmm. Bye, Shiva.
I just wanted to talk about my project a little bit.
Yeah, let's go for it. Sounds good.
I